My dear students, welcome back to our channel. In this video, I will be explaining the BSc first semester subject Chemistry as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 2 first important short question is: phenols are stronger acids than alcohols, but weaker than carboxylic acids. Explain. Answer. Phenols are more acidic than alcohols, but less acidic than carboxylic acids because of the stability of the ion formed after losing a proton, H. In alcohols, like ethanol. When ethanol loses H, it forms an ethoxide ion, CHCHO. This ion is not stable because the negative charge stays on one oxygen atom, no resonance. In phenols, like phenol, CHO. After losing H, phenoxide ion, CHO, is formed. The negative charge on oxygen gets delocalized, spread over the benzene ring through resonance, making it more stable than ethoxide ion. In carboxylic acids, like acetic acid, the carboxylate ion, CH2, formed has two oxygen atoms sharing the negative charge equally through resonance. It's the most stable, hence most acidic. Therefore, carboxylic acids phenols alcohols, in acidity. Easy tip: more resonance is equal to more stability is equal to stronger acid. Next important short question is: to explain Zaitsev's rule with example. Answer. Zaitsev's rule, also spelled Zaitsev's rule, helps us predict which alkene will form during a dehydrohalogenation or dehydration reaction. The rule says, the more substituted alkene, the one with more alkyl groups attached to the double bond, is the major product. This happens because more substituted alkenes are more stable due to hyperconjugation and inductive effects from surrounding alkyl groups. Example: when 2-bromobutane is treated with alcoholic KOH, it can form two alkenes. 1-butene from removing a beta hydrogen at carbon 1. 2-butene from removing a beta hydrogen at carbon 3. According to Zaitsev's rule, 2-butene is the major product because the double bond is surrounded by more alkyl groups, making it more stable. Easy tip: more substituted is equal to more stable is equal to major product. So, remember, Zaitsev always chooses the more substituted alkene. Next important short question is: 3. Explain the peroxide effect, anti-Markovnikov addition of HBr. Answer. The peroxide effect, also called the anti-Markovnikov addition of HBr, happens when HBr adds to an alkene in the presence of organic peroxides, like benzoyl peroxide. Normally, by Markovnikov's rule, HBr adds so that hydrogen goes to the carbon with more hydrogens. But in the presence of peroxide, the rule reverses: hydrogen goes to the carbon with fewer hydrogens. This happens through a free radical mechanism, not an ionic one. Peroxides break to form free radicals, which start a chain reaction with HBr, forming bromine radicals. These radicals then add to the alkene, producing the anti-Markovnikov product. Example: when propene reacts with HBr and peroxide, we get 1-bromopropane instead of 2-bromopropane. Easy tip: with peroxide plus HBr anti-Markovnikov. But remember, this effect does not work with HCl or high. Next important short question is: 4. Define aromaticity. Give Huckel's rule. Answer. Aromaticity is a special property of some cyclic, ring-shaped compounds that makes them very stable due to delocalized pi electrons moving around the ring. These electrons form a continuous loop of overlapping p orbitals, creating extra stability called aromatic stability. Huckel's rule. A compound is aromatic if it is 1. Cyclic, forms a ring. 2. Planar, flat shape. 3. Completely conjugated, each atom has a p orbital, and 4. Contains 4n plus 2 pi electrons, where n is equal to 0, 1, 2, 3. Example. Benzene, CH, has 6 pi electrons. Using Huckel's rule, 4n plus 2 is equal to 6n is equal to 1 satisfies the rule. Therefore, benzene is aromatic and very stable. Easy tip. 4n plus 2 rule is equal to aromatic and happy ring. So, if electrons fit this rule, the ring enjoys extra stability. Next important short question is 5. Write a note on activating and deactivating groups. Answer. In aromatic compounds like benzene, different groups attached to the ring can change how easily the ring reacts in electrophilic substitution reactions. These are called substituent effects and are of two types, activating and deactivating groups. Activating groups. They increase the reactivity of the benzene ring by donating electrons to it through resonance or inductive effect. They make the ring rich in electrons, attracting electrophiles easily. Examples of NH, OCH, CH. They direct new substituents to ortho and para positions. Deactivating groups. They decrease the reactivity of the ring by withdrawing electrons, making it less attractive to electrophiles. Examples: No, Cu, SOH, Cn, CHO. They direct new groups mainly to the meta position. Easy tip. Donators activate, ortho, para, withdrawers deactivate, meta, dot. Next Unit 2, Organic Chemistry. Long questions. First important long question is: what is inductive effect? Explain acidity of carboxylic acids using inductive effect. Answer. The inductive effect is the electron shifting effect that occurs along sigma bonds due to the difference in electronegativity between atoms. When atoms or groups are attached to a carbon chain, they can either pull electrons toward themselves or push electrons away through the sigma bonds. This shifting of electrons slightly polarizes the bond and influences the properties of molecules such as acidity, basicity, and reactivity. There are two types of inductive effects. 1. I effect, electron withdrawing effect. Some atoms or groups such as Cl, No, Cn, Cu, F, etc. are more electronegative. They pull electron density toward themselves, making nearby atoms slightly positive. This increases the molecule's acidity because it stabilizes the negative charge formed after losing a proton, H. 2 plus I effect, electron donating effect. Groups like CH, 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 CH push electrons away from themselves. They decrease acidity because they make it harder for the molecule to lose H by destabilizing the conjugate base. Acidity of carboxylic acids and inductive effect. Carboxylic acids, Cu, are acidic because they can release a proton, H, to form a carboxylate ion, Cu. The stability of this carboxylate ion determines how strong the acid is. If the substituent attached to the Cu group is electron withdrawing, I group, it pulls electrons away, reducing the negative charge on oxygen and stabilizing the carboxylate ion. Hence, the acid becomes stronger. If the substituent is electron donating, plus I group, it pushes electrons toward the Cu group, increasing the negative charge and destabilizing the ion. Thus, acidity decreases. Example: chloroacetic acid, ClCH2, is stronger than acetic acid, CH2, because chlorine has a I effect that stabilizes the carboxylate ion. Trichloroacetic acid, CCl2, is even stronger because 3 chlorine atoms withdraw more electrons. Easy tip to remember. Electron withdrawing groups increase acidity, while electron donating groups decrease acidity. Think of Cl as a helper, strong acid maker, and CH as a spoiler, weak acid maker. Next important long question is: to explain preparation of alkanes from 1. Grignard reagent, 2. Kolbe synthesis. Answer: alkanes are the simplest hydrocarbons that contain only single covalent bonds between carbon atoms. They are generally unreactive, but there are several useful ways to prepare alkanes in the laboratory. Two important methods are I. From Grignard reagents and 2. Kolbe's synthesis. 1. Preparation of alkanes from Grignard reagents. Grignard reagents are compounds of the type RNG-X, where R is an alkyl or aryl group and X is a halogen, Cl, Br, or I. They are prepared by reacting an alkyl halide with magnesium in dry ether. When a Grignard reagent reacts with water, alcohol, or even acids like CO, it forms alkanes by replacing the Ng-X part with a hydrogen atom. Reaction: RNG-X plus HO RH plus Ng, or X. Example: CHNGBr plus HOCH plus Ng, or Br. Here, methane, CH, is formed. Similarly, ethyl magnesium bromide gives ethane. Easy tip: add water to Grignard, and magnesium says bye, leaving you with an alkane sky high. 2. Kolbe's synthesis, Kolbe's electrolysis. Kolbe's synthesis is an electrochemical method used to prepare alkanes with even numbers of carbon atoms. In this method, sodium or potassium salt of a carboxylic acid is electrolyzed in an aqueous solution. During electrolysis, two carboxylate ions combine at the anode to form an alkane and carbon dioxide. Reaction: 2 RCONA R plus 2 CO plus 2 Na plus 2E. Example: 2 CHCONA CH plus 2 CO plus 2 Na plus 2E. Here, ethane, CH, is formed from sodium acetate. Easy tip: in Kolbe's synthesis, two acid parts join hands and give an even-numbered alkane. Summary table. Method: starting material reaction product. Grignard reagent RNG, X plus HO proton exchange RH, alkane. Kolbe's synthesis RCONA, electrolysis, coupling at anode R, alkane. Remember, Grignard gives any alkane, while Kolbe gives alkanes with even carbon chains. Next important long question is: 3. Explain acidic nature of acetylene. Answer: acetylene, CH, is a simple alkyne with a triple bond between two carbon atoms. One of the interesting properties of acetylene is its acidic nature, which is unusual for hydrocarbons. Why acetylene is acidic? The acidity of a compound depends on how easily it can lose a proton, H, and how stable the conjugate base is. For acetylene, CH plus H. When acetylene loses a hydrogen atom from the terminal carbon, it forms the acetylide ion, CH. The negative charge on this ion is held on an sp hybridized carbon atom. Key point: the carbon in a triple bond is sp hybridized, which means it has 50% s character. More s character means electrons are closer to the nucleus, stabilizing the negative charge on the acetylide ion. This stability makes acetylene more acidic than alkanes and alkenes. Comparison of acidity. Alkanes, Sp superscript 3CH, very weak acid, pK tilde 50. Alkenes, sp superscript to CH, slightly acidic, pK tilde 44. Alkynes, SpCH, like acetylene, more acidic, pK tilde 25. So, acetylene is much more acidic than other hydrocarbons. Reaction showing acidity. Acetylene reacts with sodium amide, 9H, a strong base, forming a sodium acetylide. CH plus 9H CH plus NH. The acetylide ion is nucleophilic and can react with alkyl halides to form higher alkynes, which is very useful in organic synthesis. Example: CH Na plus CHBr CH, propyne. Easy tip to remember. sp carbon holds electrons tight, negative charge, stable, acetylene acidic. Think more S character is equal to closer electrons is equal to stronger acid. Key takeaway. Acetylene's acidic nature is due to the stability of the acetylide ion, thanks to sp hybridization, making it much more acidic than alkanes and alkenes. Next important long question is: 4. What is hyperconjugation? Explain its applications in stability of carbonium ions and free radicals. Answer: Hyperconjugation is the delocalization of electrons in a molecule where electrons in a sigma bond, usually CH or C, adjacent to an empty or partially filled p orbital or a pi system, spread out to stabilize the molecule. It is sometimes called the no-bond resonance because the electron density from a sigma bond overlaps with an empty orbital without forming a new bond. How hyperconjugation works? A carbonium ion, carbocation, has a positively charged carbon with an empty p orbital. If a hydrogen or alkyl group is attached to the adjacent carbon, its CH sigma electrons can delocalize into the empty p orbital. This spreads out the positive charge over several atoms, stabilizing the carbocation. Example: tertiary carbocation, CH. C is more stable than secondary CH, which is more stable than primary CH. The more alkyl groups attached, the more hyperconjugation, the more stable the carbocation. Application in free radicals. Free radicals, or C times, also have an unpaired electron in a p orbital. Hyperconjugation stabilizes them by spreading the unpaired electron over adjacent CH bonds. This is why tertiary radicals are more stable than secondary or primary radicals. Example: CH, C times CH, CH times CH times. Other applications. 1. Alkene stability. More substituted alkenes are more stable because alkyl groups donate electron density through hyperconjugation to the double bond. Example: 2-butene is more stable than 1-butene. 2. Reactivity prediction. Helps explain why certain carbocations or radicals form preferentially in reactions like free radical halogenation or electrophilic addition. Easy tip to remember. Sigma electrons next to empty p orbital spread out stability boost. More adjacent alkyl groups is equal to more hyperconjugation is equal to more stability. Key takeaway. Hyperconjugation is a subtle but powerful effect that explains why tertiary carbocations, radicals, and more substituted alkenes are more stable in organic chemistry. Next important long question is: 5. Define aromaticity. Apply Huckel's rule to benzene, naphthalene and anthracene. Answer: Aromaticity is a special property of cyclic, planar, conjugated molecules where electrons are delocalized over the ring, giving extra stability compared to regular unsaturated compounds. Aromatic compounds do not behave like normal alkenes in reactions, instead, they undergo electrophilic substitution reactions. Conditions for aromaticity, Huckel's rule. A molecule is aromatic if it satisfies the following. 1. It is cyclic, forms a ring. 2. It is planar, all atoms in the ring are in one plane. 3. It has conjugated pi electrons, alternating double and single bonds. 4. The number of pi electrons fits Huckel's rule. Number of pi electrons is equal to 4n plus 2, where n is equal to 0, 1, 2. This formula ensures delocalization and stability. Application to common aromatic compounds. 1. Benzene, CH. Structure, 6-membered ring with alternating double bonds. Pi electrons, 6, 3 double bonds times 2 electrons each. Check Huckel's rule, 6 is equal to 4n plus 2n is equal to 1. Conclusion, benzene is aromatic. 2. Naphthalene, CH. Structure, 2 fused benzene rings. Pi electrons, 10, 5 double bonds times 2 electrons each. Check Huckel's rule, 10 is equal to 4n plus 2n is equal to 2. Conclusion, naphthalene is aromatic. 3. Anthracene, CH. Structure, 3 fused benzene rings in a line. Pi electrons, 14, 7 double bonds times 2 electrons each. Check Huckel's rule, 14 is equal to 4n plus 2n is equal to 3. Conclusion, anthracene is aromatic. Easy tip to remember. Aromatic rings are cyclic, planar, conjugated, and follow 4n plus 2 rule. Think of it as electron crowd control, only the right number of pi electrons, 2, 6, 10, 14, makes the ring stable and happy. Key takeaway. Aromaticity explains the extra stability and special reactivity of compounds like benzene, naphthalene, and anthracene. If a cyclic molecule fits 4n plus 2 pi electrons, it's aromatic and enjoys delocalized electron stability.